Oh, thank you.
So we're so happy to have Deepak to talk about generalized Ramsey number of cycles. Yeah, all yours.
Okay, thank you. Yes, nice to see everybody here. Yeah, there was a long time where I wasn't able to come to these because I was teaching on Fridays, but now I'm back, so that's good. Right, so I'll be talking about this generalized Ramsey numbers of cycles. So I'll try and tell you what all these things are. Okay. You've seen me give talks before. I talk a lot about Ramsey theory and Ramsey type problems. So what is the classical Ramsey problem? There's a couple of parameters, and you're given K and P. So K is a number of colors, okay? And P is like a target graph. K sub P is a target graph, okay? So given K and P, find the smallest n such that every K coloring of the edges of the complete graph Kn has to contain a monochromatic K sub P. Okay, so the classic version of this is like, how many people do you have to invite to a party to guarantee that 3 all know each other or 3 all don't know each other? And the answer to that is 6, right? So we would say that R sub 2 of K3 equals 6. Okay, I've got another example here with more colors. So R3 of K3 equals 17. What does that mean? So to prove that a Ramsey number equals, to prove that R3 K3 equals 17, you have to show 2 things. One is that it's bigger than 16 and that it's at most 17. To show it's bigger than 16, that amounts to providing a 3 coloring. In this case, R sub 3 means there's 3 colors. Okay. Providing a 3 coloring of the edges of K sub 16, so that there are no monochromatic K sub 3s, K3 being a triangle, right? Now I put that picture here. This is a 3 coloring of the edges of K16. There's 16 vertices there. They're colored in a specific way so that if you pick any 3, they don't form a monochromatic triangle. Monochromatic means all the edges are the same color. So remember, throughout all this, we're coloring edges, okay? So if you look at any 3 vertices in there, you'll find, you know, it's not monochromatic. Okay, good. But one can prove that no matter how you 3 color the edges of K sub 17, the complete graph on 17 vertices, you must find a triangle which is monochromatic. Okay, so if you color the edges of K sub 17, no matter how you want, with 3 colors, you're absolutely going to find a monochromatic triangle. Okay, in one of the 3 colors. So are we good on this? All right. Okay, so let me just rephrase the thing that I phrased it as finding the smallest n such that something happens, but I could just, if that's a minimization problem, I could look at it from this direction and say, find the largest n minus 1 such that there exists a K coloring of the edges of Kn minus 1 where every K sub P receives at least 2 colors. So remember when I showed you that picture of K sub 16, you probably forget that. Yeah, that's so if yeah, keep it up. What was it?
It was just a tablet. Yeah, but it wasn't.
It wasn't. Yeah, I don't remember seeing a tablet when we came in, but
Okay, well, I'm sorry. Well,
no, that's fine. Right. Okay, so yeah, you're looking at it from this direction. You want to find the largest n, or the largest complete graph that you're able to color with 3 colors. So every copy of a triangle, say, receives at least 2 colors, right? Okay, so what are these generalized Ramsey numbers I was talking about? Basically, you take this, the way I rephrase this, and you allow the 2 to be some bigger number than 2. Okay, so basically, yeah, you generalize it in that now you're looking for a copy, you want to color a graph so that every copy of some KP receives at least Q colors. So not just receives at least 2 colors, but Q colors, right? And then also something happens, we invert the roles of N and K. So in the versions I said, N was the objective, and you were trying to optimize the N with K fixed, number of colors fixed. And now for these generalized Ramsey numbers, for whatever reason, we invert it. So N is now an input to the problem, and K is the objective, the number of colors. So let me just state the thing here. So now, given N and P and Q, I know there's a lot of letters. Let's try now. Given we'll talk about it. So given N and P and Q, find the smallest K. K is still number of colors, right? Such that there exists a K coloring of the edges of Kn, where every KP receives at least Q colors. Okay. So this version of it was, you know what, it's honestly later I'm going to generalize it even more where this is a G and this is an H. And then I almost feel like, because there's less symbol, like less numbers floating around, maybe it's easier to understand. But, okay. So this function was first introduced by Erdős and Shira in the 70s, but then it wasn't really studied systematically until the late 90s by Erdős and Gyarfas. And what kinds of things did they prove? Oh, wait, not it. So, right. So, okay, now going back to the original Ramsey problem, R3 of K3 is 17. That's equivalent to these following 2 bounds on the F function, this generalized Ramsey number. So, F of K16, K3, 2 is at most 3, and K17 is bigger than 2, right? So you see how the K down here, the number of colors, shows up as the output of the function, because we inverted the roles of N and K. Okay, so if you could understand all the F of Kn, Kp 2s, then you would understand all the multicolor Ramsey numbers, R sub K of Kp. So if you knew this F function exactly for the Q equals 2, you know all the ordinary Ramsey ones. And if you knew it for Qs other than 2, then you know more, or you know something else. Okay, so here's the more general version. Now, before I was doing Kn and Kp, right? So now just think of it like this, F of GHQ. So now G is some host graph. Oftentimes it is Kn, but sometime in this talk, we'll be talking about Knn, so complete bipartite graphs. It's the F of GHQ is the minimum number of colors, okay, such that there exists a K coloring of the edges of G, the host graph, so that every copy of H, this little target graph, receives at least Q colors. So, right, okay, so you define this, but how do you prove anything about it? It's nice to have the want to shows laid out. And so here are the 2 want to shows. If you want to prove an upper bound on this thing, this is probably the most important thing. So, in ordinary Ramsey numbers, lower bounds are constructions and upper bounds are for every coloring something happens, right? Here it's different. Upper bounds on this thing are constructions, okay? So to prove that FGHQ is at most K, you need to find a K coloring of the edges of G so that all the copies of H receive at least Q colors, okay? And to show a lower bound, you have to prove something happens for every color, okay? So show that every K, to prove that this thing is bigger than K, you have to show that every K coloring of the edges of G contains a Q-1 colored copy of H. So when Q is 2, that's like a monochromatic copy of H. Okay, good. So it's like, remember, we inverted the roles of K and N, so now your goals are different for upper and lower bounds. Okay. So what was, now here's the previous work. Yeah, so one thing to observe is that Kn, Kp, so if your host graph is some big Kn, and you're looking to find, your target graph is K sub P, if you want every copy of K sub P to have P choose 2 many different colors, right? P choose 2 is the number of edges in K sub P. Well, then every copy of Kp has to be rainbow. But what does that mean? Now you're trying to color K sub n so that this happens. But if you ever reuse an edge on your K sub n and say Q is bigger than, at least 4, then you can put those two edges of the same color into a K sub P together, and you wouldn't have a rainbow KP. So basically that forces, if you want every copy of KP to be rainbow, then the whole graph, you have to color every edge in the KN with a different color. Okay. And going all the way down, like what I'm saying is, this P choose 2 this is the Q, right? So the things you might want Q to be are anywhere between P choose 2 and 1. But when it's 1, it's this is just 1. Okay. All right, so how does it decrease as Q moves from P choose 2 down to 1? So this is what Erdős and Gyarfás first studied, in 1997. And they proved an upper bound for these things, for every value of Q. Okay, so it's some n to a power. Okay, now that number looks a little jumbled. Just don't even, maybe you can look at that and understand what it is. Doesn't matter. Just know that there are certain, remember, Q is the thing that's ranging from P choose 2 down to 1, right? So sometimes this bound is, no good. It's not saying much. But once Q gets small enough, then this is actually, this exponent's less than 2, and it's saying something. And for particular values of Q, this expression here, this exponent will equal 1 or 2. Okay, so as you let that Q go from P choose 2 down to 1, there's some values where it equals 2 and 1. Those are called the linear and quadratic thresholds, because that's when when the behavior switches from, when you get quadratic, or when does it go away from quadratic, and when does it go away from linear, right? Right, and they proved that at those two specific locations, this bound is tight. So you can put a theta there for those two values. Okay, but then the surprising thing that was realized a couple of years ago by Bennett, Delcourt, Lee, and Postal is that it's not tight for all other values of Q. So every time that power up there is not 1 or 2, you can improve this by at least a log factor. Okay.
I'll try.
Yeah, try one more thing. Okay, so you can improve this by a log factor. Yeah.
That's a dumb question.
No, it's not. There's a lot here. Yeah, sorry.
So, do you ever consider like coloring the vertices instead of the edges?
Yeah, there are things where you color the vertices instead of the edges, but somehow it's not. That's just more akin to ordinary pigeonhole or something like that. I don't know if I'm really answering that properly, but there are versions of Ramsey things where you can color the vertices, but then maybe it's just not as interesting structurally or something. I don't know if that's completely true, but I think that like a lot of the problems just reduced to ordinary pigeonhole in that case.
And also, do you know if any of this is like applicable to algorithms?
Like, are there algorithms which can produce colorings that avoid whatever, something like that? That's a big, okay, so for small cases of ordinary Ramsey numbers, the best known lower bounds are like, constructions, and the best known upper bounds also, so these constructions are typically found either from some mix of algebraic things plus computation. Okay, so like, I'm going to look at all the Cayley graphs of a certain type and then use a computer to check something. But then the upper bounds for ordinary Ramsey numbers are like, something about for every coloring. And it's completely infeasible to check all the colorings of a large complete graph, all the. And so there's some like math that goes into reducing the search space. And then a bunch of computation that goes into like, checking off all these cases. And then you can prove like upper bounds. That might not be actually what you're asking either, but yeah, I don't know. Sometimes when you produce a coloring, there is the question of like, is that like a computable coloring, or like, is it something you could actually algorithmically get, or is it something? Is this just an existence proof? And a lot of the things I'm talking about, I think, are mostly existence proofs. Okay, but that's no problem. Okay, good. Any other questions? So I'm gonna, okay, so what else? What else was studied about this FGHQ in the more general version where the host graph doesn't have to be KN, where it could be some other graph? It turns out that mostly the other graphs that have been considered are just like KN, complete bipartite graph, which then leaves open a whole host of, for a random graph. What about for, if G is a random graph, or what if G is a complete K-partite graph, or what if, so there's all sorts of things you can ask. But anyway, so far, this thing, I think what happened, maybe it was just like, well, there's not much we can say or prove, so maybe. But anyhow, Aksinovich, Firetti, and Mubai in 2000 proved, they looked at the like basically a bipartite version of whatever I was talking about. The host graph is now KNN, complete bipartite graph KNN. And you want every copy of KPP to receive at least Q colors. So in this case, they proved some lots of things, that are all laid out in this paper. But for us, I'm going to mention one specific thing. They proved that F of KNN C4 3. So what is this? This is, you want every copy of C4 to receive at least 3 colors. You want to provide a coloring where every copy of C4 receives at least 3 colors. Right? That's what you want to, the coloring you're wondering about the existence of. And they proved a lower bound of 2/3 N. That means if you want to provide such a coloring, you have to use at least 2/3 N many colors on the edges of this KNN. And the upper bound they gave was N+1. Okay, so they provided a coloring which used N+1 colors that where every C4 saw at least 3 colors. C4 is the cycle on 4 vertices, right? Okay, ignore the bottom one. It doesn't. There's some. I don't think I'm going to talk about. All right. So then, 22 years later, there was finally improvement on that thing I just showed you. Okay, so Use and Mubai proved that the N+1 can be replaced with 2/3 N. 2/3 plus a little over 1 of N. So in other words, the answer to this thing is asymptotically 2/3 N. So what did they, remember that's an upper bound that they improved. So what they did there was provided a coloring, which only used 2/3 N many colors. And made every copy of C4 see at least 3 colors, right? Okay. So, and they also proved something about the complete graph and C4. So if you color KN, and you want every copy of C4 to see at least 3 colors, you can do it with 1/2 N many colors. Okay, and the proof method, the proof used this new method of conflict-free hypergraph matchings, which I'm going to go on a detour about. Maybe this is another thing. This is like basically one of the main topics of the thing. Forget the generalized Ramsey thing. We'll just talk a little bit about the history of this method. Okay, so this thing was introduced independently by Delcourt and Postal, and Block, Use, Kim, Kuhn, and Lichev. Both in 2022, they came out, on the same day or something like that. One of these independent, right? So it's always funny when that happens. Like if two groups just are like, we're going to prove the same theorem. It was just waiting to be proved, you know. And it's just kind of cool. Okay, so now let me tell you, before I go and talk about that, I'll tell you what we proved in our paper. So this is oh, I said it at the beginning. I should have said it. This is joint work with Patrick Bennett, Emily Heath, and Shira Zerbib. So what we proved was that we generalized the use and move by this result here. We said, what about longer cycles? This is a natural thing, you might ask. So if you want, you want to know how many colors do you need to color the edges of Kn so that every copy of CK receives at least 3 colors. Okay. And we proved basically we generalized what they did for C4 to all K. All right. So let's see. How would one go about proving this? A lower bound means I have to show that if you have a coloring where every CK gets at least 3 colors, then you need at least some number of colors to be able to do that, right? If you have too few colors, then like you're gonna see a bunch of repeats on some copy of C4 or CK, right? That's what we're trying to avoid. So if you have enough colors, there's hope you can do this. Okay. So the lower bound is, suppose you had such a coloring. All right. Then the observation is just that every color class, so imagine just all the red edges now. The red edges can't have a P sub K. They can't have a path with K vertices. Why not? Because if the red edges had a path with K vertices, then the missing edge of that path can be colored with anything, and you'd get a 2-colored C sub K, right? So that's what I wrote there. Monochromatic P sub K implies a 2-colored C sub K, right? Okay, so every color class has to avoid monochromatic P sub Ks, right? Or every color class has to avoid path with K vertices. So then the question, well, how many edges are there allowed to be in a graph that avoids a certain other graph? That's called the extremal number, or the Turan number. Which maybe you've heard of. The extremal graph theory is like how many edges can a thing have while avoiding a certain number. So EXNPK is the answer to the question, how many edges can a graph on n vertices have if it doesn't have any P sub Ks? It turns out Fodry and Shelp proved that that's at most K minus 2 over 2 times n. Okay, so if you have significantly more than that many edges, you will have a path with K vertices. Okay. But on the other hand, well, okay. So yes, but so if every color class has at most that many edges, then I can get a lower bound on the number of color classes, which is the number of colors, right? So n choose 2 is the total number of edges in Kn, and I'm splitting them into some number of color classes, each of which has at most K minus 2 over 2 times n many edges. And so I get this lower bound that the number of color classes must be at least 1 over K minus 2 times n, which is the bound we proved there, right? Okay, so that's the lower bound, that you need at least this many color classes, okay? Just by some argument about what each color class must look like. Oh, where is that?
And choose 2 is again 1 times.
Yeah, did I screw some? Oh, n minus 1, yeah, sorry. Just put a minus little o 1, or I'm being, sometimes I'll be sloppy about little minus ones and things. So I'm sorry. You're absolutely right though. Yeah. Good. Right. So now what about the upper bound for this thing? Well, that's providing a color that avoids all these 2-colored CKs. Well, the nice thing about this kind of thing is that like the lower bound, if you want your lower bound to be tight, and you know that if you want the lower bound to be tight, that means every color class has to look like the extremal example that I just talked about there. It has to look like an extremal, like it has to have as many edges as it can have without having a PK, right? If I want this thing to be tight, I need to shove in as many edges as possible in each color class, right? So then you can look to the construction for the extremal number, right? So what is the graph that has k minus 2 over 2 times n many edges and doesn't have any p sub k's, right? And it turns out that's called the extremal graph. And what it is for this EXNPK is n over k minus 1 vertex disjoint copies of k sub k minus. So a bunch of little k minus 1 cliques, vertex disjoint ones. Right? That clearly doesn't have any p sub k's, right? Each clique only has k minus 1 vertices. Okay? So that doesn't have any pk's. Right. And how many edges does it have? Well, it has this many copies of k sub k minus 1. Each of them has this many edges, and that simplifies to something like this. No guarantees about n minus 1. No, I think that's actually right. Okay. Good. So in other words, yeah, if this is the construction for this, each color class should look like this. So now my job becomes, if I want to prove if I want to provide a coloring that kind of does what I want, I know what I need to do, or what I want to do. I want to color almost all of the edges of Kn with some number of colors, n over k minus 2 many colors, so that every color class looks like this, right? So you put one of these copies down, and then you have another edge disjoint one, another set of those in blue, and then another one in green, and another one in this, right? So at the very least, I'm going to need to do that. That already feels like a hard thing to do. Can you do that? Can you take the edges of the complete graph, Kn, and decompose them into these kind of, we might call this a clique factor, right? A clique factor, meaning this is a bunch of vertex disjoint copies of k sub k minus 1 that cover all the vertices of the Kn, right? So, okay, if I'm given a big complete graph Kn, and so assume some divisibility stuff like n is divisible by k minus 1, right? I could definitely find one of them. And then I remove it, and now I've got some graph left, right? Which is like, the complete graph minus one of those. And it's like, can I find another one? Okay, maybe. Can I find another one in what's left after removing that one? Maybe. And can I do that forever until almost all the edges of, not forever. Can I do that until almost all the edges of Kn are gone? That already feels like a hard thing to answer, right? Okay, and I don't just need that. I need some special structure about them. Because what am I trying to do? I'm trying to provide a coloring of Kn, of the edges of Kn. So I want to color them so that, the red color class looks like one of those, the blue color class looks like one of those. So they're all kind of thrown down and they cover all the edges, basically all the edges. But I also need to know that they don't line up in a way that I could make a two-colored C sub K, right? That's the thing I'm trying to avoid. I'm trying to avoid two-colored CKs. So yeah, so if these, remember these are monochromatic cliques. Those are the things I'm kind of throwing down. So they definitely are only going to overlap on vertices. They can't overlap on edges because edges are only receiving one color, right? I'm decomposing the edges. So they can only overlap in vertices, but say they overlap in this kind of specific way, then I could make in this case, a two-colored C6. So not only do I need to do this, color the edges of color the edges of Kn so that every color class looks like this, that already feels hard, but I also want this to happen. I don't want specific little cycles formed out of my cliques. Otherwise okay, so how am I going to do that? Now, we'll get to this detour about conflict-free hypergraph matchings. What is this? So a Q uniform, this is just definite, Q uniform hypergraph, that just means does everyone know what a hypergraph is? Okay. It's a graph, well, you know, you have a vertex set and then you've got edges, but they don't, usually in a graph, edges have to have size 2, but now they can have size Q. Okay, so it's a bunch of blobs around Q-sized vertex sets. Those are your edges now. That's what a hypergraph is. So a hypergraph is Q uniform if all the edges have size Q. Yeah. Good, there's hexagonal. The only problem. This is a 3 uniform hypergraph. See, an edge is now a set of 3 vertices, not just 2 vertices. In an ordinary graph, edges are 2 sets of 2 vertices, right? Now I'm enlarging them to be, say, 3 vertices, Q vertices. Okay. Right. So a hypergraph is Q uniform if all the, so in general, a hypergraph can have edges of different sizes. You know, it might have edges of size 2, edges of size 5, but if they're all the same size, then we call it Q uniform. Okay. An NQR Steiner system, if people heard of these, maybe you've heard of it, or maybe not. Okay, there's this whole field of like design theory, and this is getting far from the things I actually know. But what is an NQR Steiner system? Okay, more parameters. It's a Q uniform hypergraph on n vertices. Okay, so think about it like that to start. The n and the q, it means it's a Q uniform hypergraph on n vertices, but it has a special property that every R subset of vertices is in exactly one edge. Okay, so these kinds of things, I feel like they're important in experiment design and things like that, right? You know, you want to put, you've got a bunch of people in some experiment, and you want, I'm not going to explain this right, but so you want to partition the people into some certain ways. You want to put people into blobs in certain ways so that, you know, every pair, say, is in a unique thing field. Is in exactly one thing. Okay, so let's just see if every R subset of V is in exactly one edge, then let's just do double counting. How many R subsets of V are there? This is such a strange. There's this many total. And if there's this many edges in my hypergraph, and each of them is of size Q, so, and each of them is covering Q choose R many R subsets, right? But since each of these, this isn't overcounting because each of these is appearing exactly once. It's counted exactly. Every R subset is counted exactly once on this side as well. So we must have this relation. And then you can divide this through. So the number of edges in an NQR Steiner system is exactly N choose R divided by Q choose. Okay. A partial NQR Steiner system is just you replace the word exactly with at most. Okay. So you want every R subset to be in at most one edge of your hypergraph. The existence conjecture from the mid-1800s. For sufficiently large n, so basically it's just the existence conjecture. I think it's more general than this maybe, but let's just say that. It's not even clear that it's not obvious that these things exist for any given R and Q, and then N satisfying some divisibility properties. Okay, so you know, if you're trying to make one of these Q uniform hypergraphs with all these properties, then it's clear that N can't just be anything, right? Because you might like leave some vertex out. So you know, you need some divisibility conditions, but the existence conjecture says that as long as n is large enough and satisfies those divisibility conjectures, then there exists an NQR Steiner system. There exists a way to do this. And that was a conjecture from the 1800s. Okay? Do these things exist? So what was done in 1847, Kirkman proved that N3-2 systems exist when N is admissible. We'll say N is admissible when it satisfies whatever divisibility conditions it has. Right? So Kirkman proved these end up being called Steiner triple systems. It's kind of funny that Kirkman proved their existence, but they're called Steiner triple systems. But that's how naming goes. People don't realize somebody did something. So yes, meaning there exists a 3 uniform hypergraph where every pair of vertices is in exactly one edge. That's what a Steiner triple system is, or an N3-2 system. Okay, a 3 uniform hypergraph where every pair of vertices is in exactly one edge. Okay, and Wilson proved that NQ2 Steiner systems exist when N is admissible. So Q uniform hypergraphs where every pair of vertices is in exactly one edge. But the general problem of NQR was unknown. Okay, but because this conjecture was open for a long time, so Erdős and Hanani conjecture, and this might also be called the asymptotic existence conjecture from 1963, that there exists. So remember that I said any NQR Steiner system, an exact one, no partial, any NQR Steiner system has exactly this many edges, right? Yeah.
Can you just have no edges though, for partial?
Well, yeah. Partial, yeah, no edges with it. But if you want a partial one with asymptotically the right number of edges, then it can't be. Okay, so yeah, partial ones exist, but the conjecture is about, do partial ones exist that have almost as many edges as they ought to? Okay, so I'm not requiring to cover every R subset exactly once, but maybe at most once, right? And I also want to shove in almost as many edges as an optimal one would have. Okay. Good. So that was a conjecture from 1963. Does it make sense? I should ask. Are there questions? Okay, good. Awesome. Keep trying. Nice.
Why do you think partial 6 times? Why does cross off partial?
Oh, because for this conjecture,
Yeah.
because I know that a non-partial Steiner system, every R subset appears in exactly one thing, and that means it has exactly this many edges.
So that would be, different conjecture, I guess.
Well, it's not even there. Every exact NQR Steiner system has exactly this many edges. There's no way to loosen it.
Those are not going to exist though.
Yeah, right. That's a stronger thing. The exact one is stronger, and those aren't known to exist. So this should be easier because I'm saying you don't have to cover every R subset. Some of them can be uncovered. I just want you to put in enough edges that I want you to put in asymptotically the correct number of edges. Right? Maybe you're leaving some of the R subsets uncovered, and that's okay. But you also have this property that every R subset is in at most one edge. So I'm not.
That's good.
Yeah. Okay. It's just like if you try and do it exact, then the number of edges there's no wiggle room. It's a very structured thing, extremely structured thing. It has exactly this many edges, right? And that's why you need those divisibility conditions on that. Yeah. Okay. Oh, is that my spoiler? Yes, right. Yes. So in 1985, Rodel proved that indeed these partial Steiner system, asymptotic Steiner systems exist. Okay, and this introduced a method called the nibble method, or the Rodel nibble, as it's known. And this has been a very successful method. Okay, so basically just says do something in chunks and then maybe fix some errors and then do another chunk. So you nibble away at your problem. Okay. Yeah. And then the big existence conjecture from the mid 1800s was proved by Kivash in 2014. That was like huge news. So this is the exact one. Kivash proved the exact existence conjecture. And the proof used the nibble method plus algebraic things and, 60 more pages of stuff, whatever, you know, it was hard. But, you know, I don't know if you followed any of this, like that initial paper, then there was another independent proof by another group. And then there were another independent proof by another group, and now Kivash, like, you know, a couple months ago, released a 17-page self-contained proof of the existence conjecture. Okay, now if you can read the first paragraph and understand it, then good for you. But you know, it is this can now be proved in 17 pages, self-contained, apparently. Okay, so you can take a look at that. That's as of like, you know, maybe 2-3 months ago on arXiv. Okay, great. Right. So for the asymptotic one, Pippinger and Frenkel and Rodel independently realized this is an instance of a matching in an auxiliary hypergraph. What this meaning finding these partial Steiner systems. Finding a partial Steiner system is the same as finding a matching in a particular hypergraph. And what is the hypergraph? So suppose, just as an example here, suppose you wanted to find an N5-3 Steiner system on these N vertices, okay? So what is that? That is a set of, that's a collection of 5 sets, 5 size subsets, such that every triple of vertices is covered exactly, or covered at most once, right? Okay, so what you do is you form this auxiliary hypergraph. What are the vertices of your auxiliary hypergraph? They're the 3 subsets of your ground set over there. So over here, I see, you know, if I label these vertices 1, 2, 3, 4, 5, and over here you see, you know, 1, 2, 3 is one of my vertices, 1, 4, 5 is one of my vertices. I wrote all 10, 3 subsets of there. And okay, so how many, you know, vertices are there total? N choose 3. So this is an auxiliary hypergraph on N choose 3 many vertices. And what are its edges? Its edges are all the triples. Okay, so for each 5 subset of that, look at all the 3 subsets contained within it. Draw an edge around those. That's what I did here. These are, I drew this red edge around all the 3 subsets of 1, 2, 3, 4, 5. Okay, so you're gonna have lots of edges, right? Okay. So this thing is 5 choose 3 uniform. Every edge has 5 choose 3 many vertices in it, right? Okay. And it's n-3 choose 2 regular. Why is that? Because if I pick any vertex, every vertex in here is a triple, and I want to complete it to an edge, I have to pick 2 other vertices, right? So of the n-3 other vertices, you have to choose 2 of them. So it's n-3 choose 2 regular. Now I'm going to talk about this thing codegree every once in a while. The codegree is just how many edges, fix 2 vertices. Codegree is a property of 2 vertices, okay? So fix any 2 vertices. What's the number of edges that contain both of those vertices? That's called the codegree. So you can look, given a hypergraph, you can look at the maximum codegree. It's the number of edges that contain any 2 vertices. What's the maximum of that over all pairs? Well, look, if you fix 2 triples, at most they overlap in 2 ground set points, and so they span at least 4 vertices, or 4 points, right? And so they're in at most n-4 of these edges together, right? So indeed, the max codegree is like n, which is n-3 choose 2 is like n squared-ish, and that's n-ish, which is way smaller than that, okay? That is, okay, let me write what they proved. In any, oh, I should say here. If you find, what if you find a perfect matching in here? What is it? Well, every edge in the a perfect matching in a hypergraph is a bunch of vertex disjoint edges, right? So suppose each edge corresponds to a 5 subset, right? And what does the fact that they're all that it's a matching means every 3 subset is covered exactly once, right? So perfect matching in this auxiliary thing corresponds to an NQR Steiner system, and almost perfect matching in that corresponds to an almost perfect or an almost Steiner system. Yeah, good. Okay, so but what they realized was that this is in any K-uniform hypergraph that's almost regular, it doesn't have to be exactly D regular, let's say it's almost regular, and say the co-degrees are way smaller than the degrees. Say the degrees are like D, and the co-degrees are something little o of D, so tending to 0 with D. If that happens, then you can find an almost perfect matching in any hypergraph that satisfies these two properties. It just has to be basically regular. So every vertex needs to be in about the same number of edges. And any two vertices needs to be in like smaller than that many edges together, okay? If that happens, you can find an almost perfect matching in any K-uniform hypergraph that satisfies these two things. That's that. Okay, so great. That's awesome. In other words, the Steiner problem is just an instance of a more general thing, finding a matching in a regular hypergraph. Finding a matching in a regular hypergraph with small codegrees. The girth of an N3Q Steiner system. Okay, right. So what is this about? Locally sparse Steiner systems. I'm not gonna. Basically, a Steiner system is like a hypergraph, right? The girth is some measure of local density. So if the girth is high, that means if you look amongst any set of vertices, small number of vertices, you're not going to see too many edges. Okay, that's what the girth condition is. So they call it girth. In a graph, the girth is the length of the shortest cycle, right? And that's also a local density thing, right? Because it's the smallest subset of G vertices that has G edges amongst them. That's the girth. This length of the shortest cycle, you could think about it just as a density thing, right? Cycles have G edges amongst G vertices. Right, so it's some analog of that for hypergraphs. Don't try and think about it in terms of cycles. I tried and I don't get it. But okay, so it's a local sparse condition. So Erdős in 1973 conjectured that there exist locally sparse Steiner triple systems. Okay, so not only can you find a Steiner triple system, but you can find one where if you look amongst any G points, you don't see too many edges. Okay, there was reason to believe this might be true. Locally sparse. Okay. So Bowman and Warnke and independently Glock, Kuhn, Low, and Ostis proved this asymptotically, meaning you can find an asymptotic Steiner triple system that it has high girth. And then Kwan, Sawney, and Simpkin proved it exactly. There do exist high girth Steiner triple systems. Okay, so then the natural thing this was all about Steiner triple systems, so there's this natural conjecture, do high girth, locally sparse, do locally sparse NQR Steiner systems exist? I wrote what it means there, but no J edges span at most Q minus R times J plus R many vertices. It's the analog of having too many edges amongst, for whatever reason, okay? This is the smallest, this is what you might hope to avoid, right? Like, if you make that bigger by 1, then any Steiner NQR Steiner system has those configurations, right? So 2 groups figured out how to do this asymptotically. And those names that I wrote there are the 2 people who introduced this conflict-free hypergraph matching method. Both of them basically came up with this method to solve this problem asymptotically. That was the motivation behind that. Okay, so what is it? Remember that finding an NQR Steiner system is equivalent to finding a matching in a hypergraph with small codegrees, right? So now you don't just want to find a matching in a hypergraph. You do want to find that, but it needs to be a special one. It needs to avoid these conflicts. And what are the conflicts? That would be a bunch of edges that are too densely packed in a small area. Okay, so you don't just want to find a matching in this hypergraph. You want to find a matching that avoid, so if you suppose your matching had this edge, this edge, this edge, and this edge, but when you look at those in the Steiner system, they corresponded to like a bunch of edges packed in on some points. You want to avoid that, right? In other words, you don't want that edge, that edge, that edge, and that edge to be in your matching. So there's certain configurations that you call conflicts, and your goal is to find a matching that avoids all the conflicts. And that's what they proved you can do. So the conflict-free hypergraph matching method is let H and C be hypergraphs. Okay, so H is an almost regular co-degree small hypergraph. Okay, so that's the same setup as like the Pippinger-Spencer or the, the things I was talking about earlier. And then C is a conflict hypergraph. You don't have to think about it as a hypergraph. Just think of the conflicts as a bunch of things little sub-matchings that you don't want to show up in your final matching that you're finding, right? A bunch of forbidden sub-matchings. Okay. So as long as H satisfies basically the conditions that it has to for this to be true, and as long as the conflicts are bounded in a few ways, technical ways, I'm not even going to come close to saying, but it's basically just like if you look at the hypergraph of conflicts, they satisfy some degree conditions and co-degree conditions and things just, you want them to be nice. They can't be too unruly. Like if, they can't be too big and they can't be too unruly. But if they are symmetric in some nice ways, do this. Okay, you can find an almost perfect matching in H that avoids all the conflicts. Okay. All right. So what are we doing here? Can we color? Remember, this is what we're trying to do. We're trying to color the edges of Kn so that everything looks like this. So all we have to do now, basically, is define a hypergraph H that encodes the problem we're trying to do, and a conflict system that encodes the things we're trying to avoid, right? If we can find, and then we can just apply their black box. So it becomes kind of fun if you take one of these Ramsey problems, you just have to cook up an auxiliary hypergraph, prove some technical conditions about the conflicts, you got it through. I'm simplifying it, but it's more fun to cook up an auxiliary hypergraph. That stuff is fun, right? Right. So what do you have to do? You have to define a hypergraph H such that a perfect matching in H would give us 1. What was 1? That was every color class looks like a bunch of vertex disjoint K sub K minus 1s. And the conflict system C will ensure that I don't get any of these small cycles. You can see that's kind of like another type of girth condition, right? I don't want too many of my edges to be laid out in a very particular way, right? Okay. So by the way, there's a third part here that basically that will end up coloring almost all the edges of my Kn, and then I need to color the rest. And so what do? I just use a brand new set of colors, and I have to make sure they don't mess up. And in order to do that, I use the Lovász local lemma. That's what LLL is. Okay, so I put a picture here. Maybe this is a good thing to just. What is our auxiliary hypergraph? The edges there's 2 types of vertices in my auxiliary hypergraph. There's 1 vertex in my auxiliary hypergraph for each edge of Kn. That's very much like the original auxiliary hypergraph I was telling you about first, Steiner systems, right? That's these are supposed to be the vertices of my auxiliary hypergraph. Okay, so there's 1 for each edge of Kn. And then for each vertex color pair, I have 1 of those. So I've got a bunch of these little vertices over here. This corresponds to, vertex 1 in my Kn, comma red. This one is vertex 2 in my Kn, comma blue, right? So there's 1 of these for each color vertex pair. And now what edges do I put? The way I come up with my edges on this funny vertex set is imagine any K-1 clique, monochromatic K-1 clique in the Kn. So, and I drew like, 1, 2, 3, 4 and red, right? So then I would draw an edge around the pairs 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. and the colored vertices 1, 2, 3, 4. Okay. And now let's just think. So I do that for every monochromatic k sub k minus 1. I add such a blob over here. And now imagine I can find a perfect matching in that thing. What would it correspond to? This. Okay. Because every edge would be covered exactly once. Good. And every vertex, you would never have two of these copies sharing a vertex. Two of these copies, both in red, say sharing a vertex. Because when I make one of these copies, I like swallow up 4 of these, I can't use them again in a matching. Okay, so this is cooked up in a way that a perfect matching in here would be exactly a decomposition like 1. Nice. Okay, good. And I just said some things. It's uniform. Is it regular? Yes, you have to check. There's 2 types of vertices, right? Like the colored vertices and the edge vertices, but it works out. And are the codegrees small? Yes. And so it fits. This H satisfies the H conditions from the black box that I want to use. And then, okay, I have to cook up the conflicts. I have to say that all my conflicts are, these cliques laid out in a bad way. Okay, and you have to check that those satisfy all the conditions they have to satisfy. But if they do, you're good. All right. So let's just see. I don't have time for that. We also did a bipartite graph version. And then there's some very new work where we improved our own work. So this isn't the original paper is on archive. This one we're still writing right now. But for even cycles in K and N, we had proved some bounds that differ by a factor of 2, but then with Patrick Bennett, we chomped down. We came up with a better color using this method. And it chomped it down by half. So we're halfway there. Okay. Conclusion. We also have some results for hypergraphs and some results for pads and things like that. And an important remark, similar results about that I was telling you about were independently proved by Lane and Morrison. So our papers came out on the same day. And it's another one of those things like, okay, this was bound that somebody was going to prove this. It's just a matter of who. And in fact, initially Bennett and I had a proof, and then he went and visited Emily Heath and Shira Zerbib, and he found out, oh, they also proved it. So we combined forces. So it was all actually 3 groups that were all proving the same thing. We joined forces with one of the other groups, and then the other one, we found out too late that they were working on it. So we have 2 groups. Okay, anyways. Right. Just the big thing to do here is, what are the other applications of this? Anytime you have a problem, like a coloring problem or anything like that, can you encode it as a hypergraph where you have to find a matching, where a matching in that hypergraph corresponds to what you want? And then if there's a certain structure you need, can you encode that as conflicts? So that's basically the main thing. Making these auxiliary hypergraphs is kind of fun. That's it. Yeah.
Actually, when I see the 2 hypergraph papers, there's something in common.
Yeah.
About 58 pages long.
Yes. Like both of those papers,
Yeah.
the Delco, they're both exactly 58 pages long. That's true.
Which
I
was
did notice.
daunting to me, so I didn't look at them. So
Read the first 6 pages of each of them. No, really, that's all everything I presented here is just like taking the first 6 pages of each of those and, just putting that, they're both very well written.
Okay, so the second question, you could give a one expository to talk about those 12 pages here.
That's what this was. No, no, I could. Yeah, no, I know what you mean. I will just say like, well, whatever. One of the papers used the nibble method to do it, and the other paper used what's sometimes known as the differential equations method to do it. These are 2 things that often, like, if there's a result, it's often proved in these 2 ways, either via nibble or via differential equations method. And those 2 groups proved it. We opted to use the Glock juice, etc. version because they had these things that let us do that local lemma second phase. whatever. I mentioned those extra gadgets, these test functions, things you might want to track. And then you can show not only does the matching avoid all the conflicts, but it has even more properties. It looks random. The matching that you find covers everything the right number of ways and this and that and that. What, you know, there's certain things you can track along the way. And if you have that, it's useful because then you can take the thing at the end and alter it, or not alter it, but like throw things down on top of it and you know it looks a certain way. So that's really useful. Not just having, yeah, one exists, but it's like one exists that avoids conflicts and has a bunch of kind of pseudo random properties. Yeah.
How big does N have to be, like, whatever feels good, weird, like, at least in stick are they like?
No, it's not.
that big?
Yeah, I don't think it's terrible.
Regular, like-
No, it's not like regularity stuff. No, it's not bad. There's some, you know, like if you look at the papers, whatever, there's some parameters, epsilons and things that show up, and then if this is big enough compared to that, but it's not like wacky. In fact, like the D, you know, it has to be D regular, like that. I think in one of the groups they have a weaker constraint on the D, on how fast the D has to grow. That I think. Yeah, but no, yeah. But yeah, for the existence conjecture, oh right, the newest Kivash paper says he comes up with some reasonable bounds on the N for the existence conjecture. Some reasonable bound. I don't know what they are, but you know, because existence conjecture says for N large enough, there's a Steiner system. So he gives some bounds.